Get ready for a deep dive into the crazy world of blazars.
Blazars.
Yeah. Those supermassive black holes shooting out these intense jets of energy,
Oh, right.
and they're pointed right at
Like a
us.
cosmic flashlight beam.
Exactly. And you know what's even cooler? We're going to try to figure out if these blazars could be the source of ultra-high energy photons.
Wow, that's a pretty wild idea.
I know, right? Particles carrying insane amounts of energy.
More than anything we can make here on Earth.
Exactly. And we've got this awesome scientific review article to help us on this deep dive.
Oh, cool. What's it called?
It's called Blazar Jets as Possible Sources of Ultra-High Energy Photons, a short review.
Catchy. So, where do we even begin with something like this?
Well, I think we got to start with cosmic rays.
Those high-energy particles constantly hitting Earth.
Yeah, those.
Yeah.
We've known about cosmic rays for over 100 years,
100 years, wow.
but we still don't know where the most powerful ones come from.
It's like a cosmic mystery.
Totally. I mean, we know some of them come from supernovae.
Right, those exploding stars.
And maybe some from gamma ray bursts, which are even more intense.
And then there are those active galactic nuclei.
Those supermassive black holes at the centers of galaxies.
Yeah, those are definitely powerful enough.
But when we're talking about ultra-high energy cosmic rays, or UACRs for short, it's a whole different ballgame.
Finding their source is like searching for a tiny speck of dust in a giant warehouse.
And get this, the universe actually has a speed limit for these super fast particles.
A speed limit.
Really? Yep. It's called the GZK effect.
The GZK effect, huh? Never heard of it.
Basically, imagine trying to run through a pool of honey.
That sounds sticky.
That's kind of what it's like for these UACRs traveling across vast distances in the universe.
They're slowed down.
Yeah, they lose energy when they bump into leftover radiation from the Big Bang.
Oh, I see. So if we find one with a ton of energy, it has to be coming from somewhere relatively close.
Exactly, which makes the hunt for their source even more exciting.
So where do these ultra-high energy photons fit in?
Those are a key piece to this puzzle.
How so?
Well, think about it. Charged particles like protons, they get all bent out of shape by magnetic fields in space.
Making it nearly impossible to trace them back to where they came from.
Right, but photons, they travel in straight lines.
Like little cosmic arrows pointing back to their source.
Exactly. So if we can detect these UHE photons, it's like having a map leading us right to the source of those ultra-high energy cosmic rays.
That makes sense.
But here's the catch.
What's that?
Actually detecting these UHE photons is incredibly tough.
I bet. They're probably super rare.
Oh yeah, we need massive detectors to even have a chance of catching them.
Like what?
Well, there's the Fermi Space Telescope, MAGIC, and HESS, the Tibet Air Shower Array.
A lot of acronyms to keep track of.
I know, right? They all work by detecting these things called air showers.
Air showers. What are those?
It's like when a UHE photon slams into the Earth's atmosphere, it creates this cascade of particles.
A cosmic particle explosion.
Basically. And by looking at the patterns of those particles, scientists can tell if it was caused by a photon or something else.
That's pretty clever.
Hmm.
Okay, so we've got these ultra-high energy cosmic rays and the challenge of catching these UHE photons. But what about blazars?
Ah, yes, the prime suspect.
What makes them such good candidates for launching these crazy high-energy photons?
Well, first off, we're talking about supermassive black holes here, blasting out jets of matter and energy at almost the speed of light.
They're already pretty extreme.
Right. And they're the dominant source of the highest energy gamma rays we see.
So they can definitely pack a punch.
But there's also this interesting connection to neutrinos.
Neutrinos, those ghostly particles that can pass through anything.
The very same. There's this giant detector buried in the Antarctic ice called IceCube.
IceCube.
Yeah, it actually detected a high-energy neutrino.
Wow.
And guess what? They traced it back to a blazar.
No way.
So we've got these powerful jets, gamma rays, and now neutrinos, all pointing to blazars being these insane particle accelerators.
It's starting to sound pretty convincing.
Right. It really seems like blazars could be the culprits behind these ultra-high energy photons.
But if they're so powerful, how do they actually do it? How do they rev up these particles to such crazy speeds?
That's where things get even more fascinating.
Tell me more.
There are a few main contenders for how blazars accelerate particles.
Hit me with them.
First up, we've got relativistic shocks.
Relativistic shocks.
Yeah, imagine a shock wave like a sonic boom, but way faster.
Okay, but how does a shock wave actually accelerate particles?
Think of it like a cosmic ping pong game.
Ping pong.
Yeah, particles get trapped in this shock front, bouncing back and forth and gaining energy with each bounce.
And because the shock is moving so fast, those particles can reach insane speeds.
You got it.
That's wild. What about the other mechanisms? What's magnetic reconnection?
All right, so imagine you have these tangled magnetic field lines in the jet,
Okay, I'm picturing it.
and suddenly they snap and reconnect in a more stable way.
Like snapping a rubber band.
Exactly. And when that happens, it releases a ton of energy and flings particles outwards at incredible speeds.
And that could explain those rapid changes in brightness we see from some blazars.
You got it.
Gets two. What about the last one? Turbulence. How does that fit in?
So turbulence is kind of like a chaotic mosh pit of particles and magnetic fields.
A mosh pit, huh? Sounds intense.
It is. The particles are getting jostled around and energized through random interactions, gaining energy as they bounce around.
So we've got these three possibilities.
Hmm.
Shocks, reconnection, and turbulence.
Right.
But how do we figure out which one is actually doing the heavy lifting in accelerating these particles to those ultra-high energies?
That's where we have to turn to the observations and see what clues they can give us.
Oh, that sounds interesting.
It is. For example, we've seen these patterns of variability in blazars.
Variability.
Yeah, like how their brightness changes over time. And there are these specific patterns called flicker noise and log normal flux distributions.
Uh-oh, you're losing me with the jargon.
Don't worry, it's not as complicated as it sounds.
Okay, good.
Basically, what these terms tell us is that particles are gradually being accelerated over really long distances.
So it's like a cosmic marathon, not a sprint.
Exactly. But then we also see these super fast variations in the highest energy gamma rays coming from blazars.
How fast are we talking?
We're talking changes happening in just minutes.
Minutes? That's crazy fast for something happening in a jet that's light years long.
I know. It suggests that something like magnetic reconnection might be at play.
Right, because that happens really quickly.
Exactly. So we're starting to piece together the puzzle, but there's still a lot we don't know.
Makes sense. This is cutting-edge stuff.
It is. And that's why the multi-messenger approach is so important in this research.
Multi-messenger.
Yeah. Instead of just looking at light, we also look at other particles like neutrinos and cosmic rays.
So it's like getting different perspectives on the same event.
Exactly. Like instead of just watching a movie, you're also listening to the soundtrack and feeling the vibrations.
I like that analogy.
And remember that neutrino we talked about earlier? The one traced back to a blazar?
Yeah.
That, along with the fact that we see gamma ray flares happening at the same time as bursts of neutrinos in some blazars, really strengthens the idea that blazars are these powerful cosmic accelerators.
It's like having multiple witnesses at a crime scene, each telling a slightly different part of the story.
Exactly.
Mhm.
The more pieces of the puzzle we have, the clearer the picture becomes. Okay, so we've got blazars as our main suspect, but what about those other cosmic heavy hitters, like supernovae and gamma ray bursts?
Right, right.
Could they be secretly launching these ultra-high energy photons out there?
Well, supernovae, those huge star explosions, are definitely powerful events.
Oh, yeah.
And we know they can accelerate particles to some pretty high energies.
So they're in the running.
Not so fast. Most of the research seems to suggest that supernova remnants, the clouds of debris that are left behind, they probably don't have what it takes to reach those extreme energies needed for UHE photons.
So supernovae are kind of like the minor leagues of cosmic particle acceleration?
Yeah, I guess you could say that. They're important, don't get me wrong.
Sure.
But they're probably not hitting those ultra-high energy home runs.
Okay, supernovae are out. What about gamma ray bursts? Those are even more intense, right?
Oh yeah, gamma ray bursts are like the universe's biggest fireworks show.
Really?
Totally. They release this incredible amount of energy in a really short amount of time, just a few seconds, maybe minutes.
Wow. So they could be capable of producing those UHE photons.
It's possible, but there's a catch.
What's that?
Gamma ray bursts are super short-lived. They just flare up and then disappear.
So it's like trying to catch a lightning bug in a bottle.
Yeah, exactly.
Yeah.
Detecting those UHE photons from a gamma ray burst would be ridiculously difficult.
So we've ruled out supernovae and gamma ray bursts. That leaves us with blazars.
Right, the steady beams of energy.
But here's another question that's been bugging me. If blazars are shooting out these UHE photons, why haven't we seen more of them? Shouldn't they be raining down on us?
Well, even though blazars are incredibly powerful, the chances of a UHE photon actually getting created and then traveling all the way to Earth without hitting anything along the way, it's incredibly small.
So it's like winning the cosmic lottery.
Exactly. Plus, our detectors aren't perfect either.
They can't catch everything.
Right. They have limitations in how sensitive they are, and they can only observe a small part of the sky at any given time.
So it's a combination of the events being super rare and our technology not being quite up to snuff yet.
Yeah, pretty much.
But we're getting better, right?
Oh, definitely. New, more sensitive detectors are being built all the time.
That's good to hear.
And we're constantly developing better ways to analyze the data, too.
That's awesome. So are we close to solving this UHE photon mystery?
Hmm. I don't know if I'd say we're close to solving it,
Okay.
but we are making some really good progress.
That's what matters.
And remember, this is still a pretty new area of research.
Yeah.
We're just starting to really understand these ultra-high energy particles and how they're made.
I think it's amazing that we're even able to study this stuff.
Me too.
You know, earlier we talked about how studying UHE photons could help us understand physics beyond the standard model.
Right, right.
That's a pretty big deal, isn't it?
Oh, absolutely.
Hmm.
The standard model is our best understanding of the fundamental particles and forces that make up the universe.
Uh-huh.
But we know it's not the whole story.
What do you mean?
Well, there are things out there that the standard model just can't explain,
Like what?
like dark matter and dark energy.
Oh, right. Those are still big mysteries.
Huge mysteries. And by studying these ultra-high energy particles with energies way beyond anything we can make here on Earth,
Yeah.
we might find clues about those missing pieces of the puzzle.
So it's like we're getting a glimpse into a whole new realm of physics.
Exactly.
That's pretty mind-blowing.
It is. It really is.
You know, it's just incredible to think about all the stuff we still don't know about the universe. It makes you wonder what other secrets Blazars might be hiding, right?
Definitely. And don't forget, it's not just about the UHE photons.
Oh, right.
Blazars are producing neutrinos and cosmic rays too, and these things are all connected.
So we need to study them all together.
Exactly. That's what the multi-messenger approach is all about.
It's like listening to a whole orchestra, not just one instrument.
That's a great way to put it.
And the more we listen, the more we'll understand the music of the cosmos.
Couldn't have said it better myself.
All right, I think we've covered a lot of ground today. We've talked about cosmic rays, blazars, and those crazy UHE photons.
It's been a wild ride.
It has. But before we wrap things up, I want to talk about one more thing.
Okay.
The source material mentions a connection between UHE photons and the cosmic microwave background radiation.
Ah, yes, the CMB.
Can you tell us a little bit more about that?
Sure. So the cosmic microwave background radiation, or CMB for short, is this faint afterglow of the Big Bang.
Wow, an afterglow from the Big Bang.
Yeah. I know, right? It's this radiation that fills the entire universe.
Amazing.
Like a time capsule from the very early universe.
So how does it connect to UHE photons?
Well, remember that GZK effect we were talking about?
Mm-hmm.
Those UHE photons can interact with the CMB as they travel through space.
Oh, right.
And those interactions can actually drain energy from the UHE photons coming from really far away.
That's like a cosmic speed bump.
Exactly. But there's another cool thing.
What's that?
Those interactions can also create other particles, like electron-positron pairs.
And then what?
And then those particles can go on to interact with other photons in the CMB, creating a cascade of lower energy photons.
Whoa, it's like a chain reaction.
It is. And by studying these cascades, we can learn a lot about both UHE photons and the CMB itself.
It's amazing how everything in the universe is connected.
I know, right?
By studying these UHE photons, we're not just learning about blazars, but also about the very fabric of space and time and the leftovers from the Big Bang.
That's the beauty of astrophysics.
Yeah.
Everything is interconnected.
I love it.
Me too.
This has been an incredible journey, but I think we need a little break to let all of this amazing information sink in.
Agreed.
We'll be right back to wrap things up and explore what this all means for our understanding of the cosmos, so don't go anywhere.
And we're back for the final stretch of our cosmic adventure.
Ready to wrap things up?
Yeah, we've covered so much ground today. Blazars, cosmic rays, ultra-high energy photons.
It's been a whirlwind tour of the high-energy universe.
It really has. So let's zoom out for a second and look at the big picture.
Sounds good.
What are the biggest takeaways from our deep dive into the world of blazar jets and those mysterious ultra-high energy photons?
Well, I think one of the clearest things we've seen is that blazars are just incredibly powerful cosmic accelerators.
They're like the ultimate particle smashers.
Exactly. And we see evidence for this in their gamma ray emissions, those neutrinos we talked about. And even the theoretical models suggest they could be behind these UHE photons we've been trying to track down. So even though we haven't definitively proven that blazars are the source of those UHE photons,
Right.
it's looking pretty likely.
The evidence is certainly piling up, and the search is definitely still on.
And new telescopes and detectors are coming online all the time.
Yeah, which is super exciting.
It's going to give us so much more data to work with.
And help us get a better handle on what's really going on with these blazars.
Earlier we touched on how studying these blazars could even help us understand physics beyond the standard model.
Yeah, that's one of the most mind-blowing things about this whole thing.
It is. It's like these UHE particles, they carry energies that are just mind-bogglingly high, way beyond anything we can create in our labs.
Way beyond.
So by studying them, we might find clues to things like new
Right.
particles, new forces.
Maybe even new dimensions.
Yeah, it's like the universe is running its own physics experiments.
We get to watch.
Exactly. But some of our listeners might be wondering, why should we care? What's the relevance of all this to our everyday lives?
Well, that's a question that comes up a lot, and it's a good one.
Yeah.
At the end of the day, this type of research is all about expanding our knowledge.
Understanding our place in the universe.
Exactly. It's about unraveling the mysteries of the cosmos.
It's about the pursuit of knowledge for its own sake.
You got it. And throughout history, that pursuit has often led to amazing technological advances that we benefit from today.
It's true.
Who knows what incredible applications might come out of our understanding of blazars and these UHE particles in the future.
It's exciting to think about all the possibilities.
It is. It's that sense of wonder and curiosity that keeps us going, keeps us exploring.
Well, on that note, I think it's time to wrap up our deep dive.
Time flies when you're talking about blazars.
It really does.
I know.
We've explored the mystery of cosmic rays, the mind-blowing power of blazar jets, and the challenges of trying to catch those ultra-high energy photons.
We've even talked about how all of this might connect to new physics beyond this standard model.
And we've seen how the multi-messenger approach is giving us a whole new way to study the universe, a way to combine information from different sources.
It's like putting together a giant cosmic puzzle, piece by piece.
Exactly. So before we sign off, I want to leave you with one final thought to ponder.
Okay, I'm listening.
If blazars are these cosmic cannons shooting those high-energy photons across the universe, what other cosmic events might be connected to them?
That's a good question.
Are there links out there that we haven't even considered yet? What other secrets might be lurking in the hearts of those blazars?
Plenty to think about.
It's a big universe out there, full of mysteries waiting to be uncovered.
And we're just getting started.
Thanks for joining us on this incredible journey into the heart of blazars.
It's been a pleasure.
Keep looking up and keep those questions coming. Until next time.